In the previous few slides, we have gone through some simple examples. Now I have a few examples on a more complex mechanical system, and then let's try to derive the mechanical model of it. In this slide, you can see a mass supported by two springs in serial connection to the ground. And then the mass here is excited by an input force ut. So the input force u here is the input to the system. And then obviously, because of the flexibility of the spring that support the mass will vibrate. But remember, in here there are two springs connected in serial, and because of the flexibility of these two springs, the junction between these two springs will also move differently than the motion of the mass. So as an illustration, you can see how the system will move in this very short video. Okay, now as you have seen the animation of the system, we can start to derive the model of the mechanical system. So in here, if you see, the mass will move. Let's say in here we indicate the motion of the mass by x, and then the junction between these two springs we can indicate it by y. Let's say these x and y will move differently. So in this case, you can see this as a system which has one input, which is force u, and two output, which are x and y. And we should be able to model the relationship between u and x, u and y. But of course, in our case here, we are interested more on how the mass is moving. So we will derive more the relationship between u and x. Okay, now let's break down each element to derive the mechanical model. In the upper right corner of this slide, you can see again the mechanical system schematically there. And then now I will analyze the first spring, the spring K1, independently. So I will analyze this one first. Imagine that the mass is moving to the right after I apply an input force u. So as indicated by x here in the upper right figure there. And because of the flexibility of the spring K1 and K2, the junction between these two springs, which I indicated as y, let's say this point, the junction of these two springs is also moving to the right, but the motion is y, it's not x. So y is moving differently than x because of the flexibility of K2. But let's assume at this point y is moving also to the right. So I can analyze the spring K1 now, as you can see in the left figure there. The right end of the spring K1 is moving to the right by y. If the left end of this spring is kept fixed to the ground, so basically this spring is stretched, right? If you stretch a spring, what does it mean? That means you apply force to the spring to the outward direction, and the force that you apply to these springs is proportional to their relative deformation. So the force applied to the spring basically is equal to K1 times y, where K1 is the spring constant and y is the relative deformation. So our analysis on the first spring is finished here. We move to the second element, spring K2. Here you can see the spring K2. I draw it here again individually, yeah, spring K2. So based on our previous assumption in the previous slide, the left end of spring K2, which is equal to the right end of spring K1 is moving to the right by y. And then now what happened to the right end of the spring K2? The right end of spring K2 is connected to the mass. While in our assumption, the mass is moving to the right side by x. What does it mean? This means the right end of spring K2 is also moving to the right by x. Now what happened to the force applied to the spring? The force applied to the spring depends on x and y. Let's take an assumption here. If x is greater than y, just take an arbitrary assumption here. I just take an assumption that x is greater than y. What will happen if x is greater than y? The right end is moving to the right much more than the left end moving to the right. What does it mean? That means the spring is stretched, isn't it? The spring is becoming longer because the right end is moving more to the right than the left end moving to the right. So the spring essentially is stretched. How do you stretch a spring? You stretch a spring by applying a force in outward direction. So in here, there is a force applied to the spring in the outward direction. And the force, the norm of the force, is proportional to the relative deformation. Since x is greater than y, this is our assumption, so the relative deformation is x minus y. So the force applied to the spring is equal to K2 times x minus y. Again, of course, here K2 is the spring constant of the spring K2. Now, let's put more attention on the left end of spring K2. If you look at the figure again of the system, the left end of spring K2 basically is the right end of spring K1. In our previous analysis in the previous slide, at the right end of spring K1, there is a force pointing to the right, which is equal to K1 times y. If we transfer this force, the force acting on spring K1 to spring K2, then the force of K1y will act as a reaction force to spring K2. If K1y in spring K1 is pointing to the right, so in spring K2 it is pointing to the left with the same value, K1 times y. This force basically is the same as this force because they are acting at the same point, acting at exactly the same location. So essentially these two forces are equal. They are two identical forces. So from here you can conclude that this force, K2 times x minus y, is equal to K1 times y. So these two forces are equal because they are basically the same forces. So from here you can derive the first equation, that K2 times x minus y is equal to K1 times y. This will be our first equation. Let's call it as equation 1. Now, the next element is the mass. If I draw the mass again here, looking at the mass, the right end of spring K2 is attached to the mass M. So there will be a reaction force to the mass M, which is equal to the applied force to the action force on spring K2. which is equal to K2 times x minus y, this force. But to the mass, this is acting as a reaction force. So to the mass, this force is pointing to the left side. So when I transfer this force to the mass, I will get this force. On the right end of this mass, I have an input force. I have an applied force of ut. So I have already put all of the forces acting on the mass here, on the mass m there. And then we can apply the Newton's second law. Newton's second law says all of the total forces acting on the mass will be equal to the mass times the acceleration. Since the mass is moving to the right by x, so pointing to the right direction is a positive direction. So mx double dot will be equal to positive u minus k2 times x minus y. So at the end, we will get this equation. And this basically is, I define it as the second equation. Now, let me rewrite again the first equation. You still remember the first equation? I can manipulate the first equation into something like this. And then from this equation, I can express the y, the motion of y in terms of x, as you can see in the second equation. Now, if you go back to equation 2, this is the equation 2, I can substitute the y value to the y in the equation 2. So at the end, I will only have an equation that correlate the input u and the output x here, right? At the end, by just a simple mathematical manipulation, I can derive the equation of motion, the differential equation that model the mechanical system that we are talking about. So if you look at this is the final result of the differential equation to model the system. If you look at this equation, u represent the input to the system and x represent the output, the displacement output of the system here. As you can see, this is basically a differential equation which also involves the second derivative of the output x. So how did we derive the model just now? You still remember? We derived the model by analyzing the forces at each element individually, the springs as well as the mass. You still remember there is one assumption that we took when we derived the differential equation. The assumption that we derive when we analyze the second spring. The assumption that we took before is when we assume the right end of spring K2 is moving more than the left end of the spring K2, or x is greater than y. This is the assumption that we took on when we derived the differential equation of the system. Now, how if we take different assumption? So the assumption that we took before, we just took it arbitrarily. We just assume it x greater than y. How if we take different assumption? How if we take an assumption that x is less than y or y is greater than x? Let's analyze again the spring K2. If we assume y is greater than x, what will happen to spring K2? The left end is moving more to the right than the right end. That means spring K2 is compressed, isn't it? If spring K2 is compressed, What is the direction of the force applied to the spring? Of course, the force is pointing in inward direction. And the applied force that is pointing in inward direction will be again proportional to the relative deformation. But in this case now y is greater than x, so the relative deformation will be y minus x, pointing to inward direction. So the force applied to this spring is equal to K2 times y minus x. But the forces are pointing inward direction. So if you compare these two analyses using two different assumptions, the force are pointing at a different direction, at the opposite direction. And the norm of the force is also inverse here. The first assumption, from the first assumption, we have the force is equal to K2 times x minus y. If we take the second assumption, the force is equal to K2 times y minus x. Again, from here, the left end of spring K2 basically is the right end of spring K1, right? And since these 2 points, this point and this point are identical, these are the same point, so I can transfer this force, the force from spring K1 to spring K2, because this force K1y and K2y minus x essentially are the same. But if I transfer the force K1y to the second spring, of course I have to put a different direction of the force, because it will be the reaction force to the spring K2. So when I transfer this force to K2, then the reaction force basically is to the pointing to the left direction. These two forces are the same. So from this analysis, I know that K2 times y minus x is equal to minus K1 times y. Let me rewrite it again here. And then if I do again a mathematical manipulation, I can rewrite this equation into something like this. If you look at this equation is basically the same like this equation. These two equations are identical. What does it mean? We have the same equation at the end. No matter what assumption that you take, the resulting equation will always be the same. So don't worry too much with the assumption. You can take any assumption when you derive the model. The main thing that you have to keep in mind is that you have to be consistent with your assumption from the beginning till the end. So again, don't worry too much with assumption. You just take any arbitrary assumption. As long as you are consistent with your assumption, you will have the same result at the end. Let me go back to the differential equation that relates the input u and the output x. So this is the differential equation that we derived in the previous two slides. Now, if you want to analyze it further, let's say if you want to derive the transfer function, you know how to do that. We discussed this in the previous topics. I can convert this differential equation form of the model into transfer function form. How to do that? Of course, just simply take the Laplace of this equation. So you just Laplace transform both sides, the left side and the right side. And then after that, you take a zero initial condition to the Laplace transform form. After that, of course, you just simply have to find the ratio between output and input in Laplace domain, and then you will get the model in transfer function form. So this is basically on how to derive the mathematical model from a mechanical system for a complex mechanical system. So what we did just now, we try to model it when we have a system supported by 2 serial spring. At the same time, using the similar analysis, you can also derive the mathematical model of a system when the mass is supported by parallel springs. So you can try it by yourself for a system with a mass supported by parallel spring, and then you will see the difference between serial spring and parallel spring.